Real-world problems rarely hand you one neat variable. They give you dozens or hundreds, interacting all at once without any obvious pattern. This animated diagram displays the mathematical version of that exact chaos, a stacked system of 3 linear equations with variables x1, x2, and x3. Trying to solve this by randomly substituting numbers is functionally impossible. You would be guessing forever. Instead of guessing, mathematicians rely on Theorem 1. This theorem states that equivalent systems of linear equations share exactly the same solutions. If we alter the equations using valid mathematical moves, the final answer remains completely intact. Our ultimate goal is to mechanically transform a messy system like this into a drastically simpler state without losing the underlying truth. We strip away the letters and equal signs. All the crucial data is held in the numerical coefficients, which snap into a neat rectangular grid. This structure is an m by n matrix, where m is rows and n is columns. Dropping the algebra is a massive relief. We can stop worrying about isolating x or y and focus entirely on manipulating the raw geometry and numbers of the grid itself. By translating equations into this format, we can apply a standardized, algorithmic set of rules to move the data into a solvable state. So, the data is locked in a matrix. How do we actually alter it without breaking that rule of equivalency? We use 3 specific moves, known as elementary row operations: multiply a row by a scalar, add a multiple to another row, or simply swap 2 rows. Watch this animated diagram of a 3 by 3 matrix. When we multiply the top row by a scalar and physically drop it down to add to the second row, that targeted coefficient becomes a 0. We are effectively eliminating unwanted data points. Those 3 moves are the only tools required to safely navigate, unravel, and eventually solve any linear system in existence. We apply those operations repeatedly with a very specific finish line in mind, a state called the row-reduced echelon matrix. This forms a clean staircase pattern. The first non-zero row entry is 1, making the rest of its column 0. The identity matrix is the perfect example: diagonal 1s, 0s elsewhere. If a non-zero appears beneath a 1, the rule breaks. Variables aren't isolated. Thankfully, Theorem 5 guarantees that absolutely every matrix can be successfully manipulated into a row-reduced echelon form. Reaching this strict staircase structure perfectly isolates every variable. At that point, the solution simply reads itself off the page. Solving a single system is useful, but often we need to chain multiple transformations together. To do that, we use matrix multiplication. As this diagram illustrates, the mechanics are counterintuitive. You don't multiply straight across. Instead, an entire horizontal row in the first matrix slides over, turning 90 degrees, and multiplying against a vertical column in the second matrix. Matrix multiplication is associative. Grouping doesn't change the outcome. But if they swap physical positions, multiplying matrix B by A produces a completely different result than A times B. It is explicitly not commutative. The multiplication order dictates the final product. Treating this process like grade school arithmetic will permanently corrupt your system. It is a powerful engine for combining data, but only if you respect its directional rules. Sometimes a mathematical transformation goes too far, or we need to trace our steps backwards. We need a way to perfectly undo the process. As this diagram shows, this requires invertible matrices. An n by n matrix A is invertible only if there exists a matrix B, where multiplying them together yields a pristine identity matrix. They cancel each other out. This leads to a central result in the theory, outlined in Theorem 12. An n by n matrix is invertible if and only if it is row equivalent to the identity matrix. We started with a chaotic system of equations. We abstracted it into a matrix, manipulated it via row operations into an echelon form, and utilized multiplication and inverses to systematically extract the final solution. Solving for a single x is only the beginning. The real value lies in a universal, algorithmic pipeline that can translate chaos into clarity for infinite variations of a problem simultaneously. These foundational tools form the bedrock of higher mathematics, beautifully detailed in the classic Hoffman and Kunze text seen here. Let us know in the comments which chapter of this textbook, or any other math book, you want decoded next, and be sure to like and subscribe for more deep dives into the mechanics of math.